Swayam Prabha. Digital India. Educated India.
So now the next one is pressure. Here you will have some pressure P1. Here you will have, you can say P0, P1, or P1, P2. So let's say we call it at Z equals to P0, and here we call it PL. So because of pressure there will be some term. So we know the pressure force will be P0, and area we know is 2 pi r delta r, or we have been seeing dr. So let's call it dr. And then here it has to be PL, what is coming in and what is going out. R, dr. Okay, so this is not 0. Next is so pay attention here. So next is due to shear stress, or we say due to viscous dissipation rather. So because of fluid viscosity, there is some certain momentum coming in, coming out. So what we define is essentially stress, shear stress. Let's say anywhere here in this direction. So shear stress term will be what? We can write this as in the direction of Z, because this is the direction of fluid flow, but the momentum is being transferred in R direction, right? We know that R equals 0, you will have maximum flow, maximum velocity, and as you go to the wall, the velocity becomes 0. So momentum is being transferred in this direction from 0 to R. So this will be tau RZ. Okay. So momentum that will come in here, and then it will go out from this R plus R. So this will be tau RZ times the area. Now area is not this cross section area, rather for shear stress, this area we need to take, area parallel to the force. So now this area will be what? That it will be 2 pi r L. Okay. So this whole thing we can take it at R, and then what comes out is tau shear stress, and then also this area at R plus dr or delta R. Okay. So in this case, here you need to be a little careful. 2 pi L is constant, but then you will have tau R becomes here R tau RZ at R equals R, and then this minus R, this whole thing, R tau RZ means R plus dr. Okay, so this is R, here also R. So please note that this R you cannot take out, because otherwise you need to write R plus delta R plus dr and so on. So we are just writing this R and tau RZ together. It helps with math. Okay, so are we missing anything else? Yeah, of course. We will have gravity, right? So gravity will help this flow. So it's acting in plus Z direction. So what we can write, gravity will be just m times g. So m is your whatever is density, it's incompressible, so that is fine. The volume will be 2 pi r dr. So 2 pi r dr L. This is your density, volume, and then g. Okay. So just to simplify, you can write that 2 pi r L dr g and so on. So it's the same thing. Okay. So this term we don't need to consider. This is already taken care of. So we will have 3 terms, 1, 2, 3 in your momentum conservation. Okay. So let us start with simple one. So 2 pi r dr p naught minus pl. That is your here. So you just do this term common. Now viscous, you have to be a little careful. 2 pi l, and then you will have r to rz at r minus r to rz at r plus dr. What else? Then you will have gravity plus 2 pi 2 pi r l dr g, 2 pi l r dr g anywhere, 2 pi l g r dr, and that this whole thing should be 0. Okay. So now if we divide divide this whole thing by 2 pi l, divide by 2 pi l and dr. Okay, so if you do that, then this will become p naught minus pl. 2 pi r dr is 2 pi dr is gone, so this will be by l. Of course, there will be a term called r here, and then 2 pi l dr, so this will become r to rz, r minus r to rz at r plus dr, and then this is divided by 2 pi l dr, so delta r you can write. I think that would have been easier. Made more sense. So now here you can write 2 pi l dr, so you can write g times r. So if you see if you can take these two terms that side on the right hand side, then this will become, you can write this as r t. So this whole thing you can write as minus d by dr r to rz, right? Because this is to r to rz at this minus this, and then so on. So you can write that. So change the color back to black. Okay, so what we get it from here, you take it from right side, these two terms right side, then this negative sign will be gone. So d by dr at this r to this thing becomes p naught minus pl by l plus g. Negative sign is gone from here, and then both multiplied by r. So this. Okay. So this will give you r to rz is equal to so you can take that side and integrate. So this will give you p naught minus pl by l plus g. Are we missing something? Okay, yeah. So here you should have density missed from here. So you should have density here. So we are missing density. So this will be rho g, and this will become r. If you integrate, this will become r squared by 2. And let us keep this as indefinite integral. So that will be r squared by 2 plus c1. Yeah. So this will become yeah. So you have a c1 is a constant, and however, if you you still have this. Let's first write it completely. So this will be tau rz will be this p naught minus pl by l plus rho g. You divide by r, so this will become r by 2 plus c1 by r. Okay. So if you look at if you go back here, what we have seen is in because of symmetry, we saw that the intuitive, from our flow description, we saw that the flow has to be maximum at the center, and because of symmetry, the slope of velocity, has to be 0 here. So what essentially that means is dvz by dr at r equals 0, that is at center, has to be 0, and that would mean that tau rz at r equals 0 has to be 0. So if you do that in this equation, then that would mean that C1 has to be 0, right? Because of this. So what we can write essentially is tau rz is P naught minus PL by L plus rho G, right? And by into R by 2. Okay. So this is the shear stress. Okay. So if we look in your flow, and if we plot shear stress, then we start with R. So R equals 0, it's 0, and as you go to R, this will become maximum at the wall. Okay. So something like this, it will start with 0, and then this will be tau max, right? So one can write tau rz max is equal to tau rz at R equals R, so that is at the wall, and then this value is P naught minus PL by L plus rho G by 2. Okay, so now we know what will be the shear stress at the wall. That solves our one problem. Now other thing is we want to know what will be the flow rate and velocity. So we continue from here. So Rz can be written as minus mu dVz by dr, right? So this is from assuming Newtonian fluid, we can write this. Okay, so this will be P naught minus PL by L plus rho G R by 2. Other things are it's constant. So now if you do integration both side, taking dr here and so on. So if you do that, you can say Vz should be equal to minus. No, you can first write minus 1 by mu. You can first take it here, so that will become minus 1 by mu P naught minus PL by L plus rho G, and then when you integrate this will become R square by 2, so that will give you R square by 4. Okay, and then there will be some other constant C2. So we need to look for another boundary condition. Condition number 2. So we had boundary condition 1 here. So you can see that once you come up with do this balance equation, you integrate it, and then you have to look for some boundary conditions to solve for the constants. In this case, we need to look for second boundary condition. So if you try, we have seen that from our flow description that the velocity profile looks something like this. So that means at Vz at R equals R has to be 0 because of no slip condition. Right? So this becomes your boundary condition 2. So if you apply this boundary condition 2, then Vz at R equals R will become 0. So your C2 will be just this number times minus 1. So that will become 1 by mu P naught minus PL by L plus rho G times capital R square by 4. Okay. So once you have that, you can substitute C2 here, and you can easily see that this term is common here. So Vz is equal to what? 1 by mu P naught minus PL by L plus rho g. So this is common in both. Then this will be r squared by 4. So you can take that 4 common as well. And to write it, more conveniently, you can write is 1 minus r squared. Right? R squared also we take common. So okay. So this essentially gives you, you can essentially see that, if you put r equals 0, this will be the maximum, right? So one can find Vz max will be P naught minus PL by L. Sorry. P naught minus PL by L plus rho g, then r squared by 4 mu. Okay. So this is your Vz max, and from here it actually follows parabolically, and then at the wall this becomes 0 as we have seen in the condition. Okay. So this is your velocity profile in the radial direction. Okay. So Vz you can also write, in other words, Vz also you can write as Vz max times 1 by r square, 1 minus r square, r square, right? It is the same thing. So okay. And this Vz max is constant for given geometry, given pressure condition. It does not have any dependence on a small r. Okay. So now that we know this, what we actually want to know was volume flow rate. So volume flow rate in for this given control volume, what we can write dB. So area is 2 pi r dr, and then whatever is Vz. Okay. So this is your volume flow rate. So area is 2 pi r dr, and then you have volume flow rate. So volume flow rate is dr we will write here. Okay. 1 minus r square by r square times dr. So if we integrate this Vz, here it should be Vz max. That becomes constant. So if you integrate this, r equals 0, of course you don't have any volume flow rate. So across the cross section we want to know what is the volume flow rate. So we from here. So volume flow rate for you is, of course this r has to go in. So if we integrate this, we have to put r here. This will be 2 pi Vz max r minus rq by r square dr 0 to r. Okay. So 2 pi Vz max, and then once you integrate this will be r squared by 2 minus r4 by 4r square from 0 to r. So that becomes 2 pi Vz max. We can substitute as this. So this will be, before we do that, let us just evaluate this. This will become easier. So if we do this will be r squared by 2 minus r squared by 4, right? So it will be r4 by r squared, so that becomes r squared by 4. So as you can see, this will be r squared by 4, right? So we know from here Vz max is P naught minus PL by L plus rho g, and then you have r squared by 4 mu, r squared by 4 mu, and then this term has to be there, so that is r squared by 4. You can cut this 2, so that does give you the volume flow rate is equal to this P naught minus PL by L plus rho G by R4 by 8. Okay, so this is a famous equation for flow through a tube known as Hagen Poiseuille. So pardon me for spelling if I'm Hagen Poiseuille equation. What you see is, it would not have been very intuitive. A volume flow rate, if you have a given pressure drop, the volume flow rate actually goes with R4, right? It does not go with R square. It goes with R raised to power 4. Okay. Other things are more or less intuitive. So especially, if you have for a given tube, given fluid, if you increase the pressure drop, then you will get more flow. So this V dot is flow rate meter cube per second. Okay. So if you have, but if you have, let's we'll see, in the practice problem we'll see the application of this. So this is a summarized here in like nice typed form. So the shear stress came out as this. Volume flow rate we found out, and then from volume flow rate you can find the average velocity. Okay, so average velocity will be essentially whatever is volume flow rate through a cross section by area. So V dot we know is we found from integration, right? But we can write this in the form of AB average. So if you know V dot, then you can find average velocity. Okay, and then this is your average velocity. Okay, average velocity goes with R square, but your volume flow rate goes with R raised to 4, because this goes to R with R square, and then you multiply by area. So of course, naturally it goes with R4. Okay. So this is very useful equation, and whole exercise also gave, hopefully gave you some confidence on how to start with basic. You recall we started with basic equation: momentum in, momentum out, rate of momentum in, momentum out. Then the task is to identify what are the important terms or relevant terms here, and then here we found from mass balance that this is essentially velocity remains same, and that was in the flow description as well. Other things responsible are pressure drop, flow, this dissipation due to this viscous flow. Because of viscosity there is some dissipation, and gravity. We had all these terms in energy equations as well. And then we just did the math, which is not very complicated if you just follow step by step. The only tricky thing is, here we have to be careful with R. Okay, then we first find in this case we found the stress equation for stress, and then from the stress equation we can find the velocity. You will see that this theme, first time we have come up with an analytical equation in this course. So we'll see that you will see that we'll follow similar method in most of the problems. So you start with basic equation, you make certain assumptions, etc., and then you find certain boundary conditions that here you have two boundary conditions to find the constant. Okay, so this is the method we'll follow in this course in general. So I hope you have understood this clearly. Okay, so let us do this simple practice problem. So for a given pressure drop per unit length in straight tube of these two diameters, it can be either 10 mm or 20 mm. You can assume steady state incompressible fully developed flow regime. So based on the discussion we just had, what would you like to say about the volume flow rate in these two tubes? Should they be same? The pressure drop is fixed. Remember that. So the larger diameter tube have a twice large flow rate, or a smaller diameter tube should have higher flow rate. Okay, or should this large diameter tube should have a 16 times larger flow rate. So based on this, the volume flow rate hanging partially equation here. So based on this, what can you say if your P naught minus PL by L, this is fixed, and then you have a different size of tube, so 10 mm versus 20 mm. So if you increase the diameter, if you take larger tubes, should you get more flow rate or should you get smaller flow rate? Okay, so just think and answer this. With that, this is the end of lecture 5. Thank you for your attention. We'll see you in the next lecture. Thanks.